So I'm going to be talking about topology of permutation patterns, and this is based on joint work with Priyavrat Deshpande and Anurag Singh. Okay, so the basic idea is that we will start with a permutation pi and associate a simplicial complex X pi to, so topological space. And the goal is to find the relations between the structural properties of pi and the topological properties of X pi. And so this is a common theme in topological combinatorics. So that we're all on the same page, I'm going to quickly define a simplicial complex. So a simplicial complex on the vertex set of numbers from 1 to n is just a collection of subsets that is closed under inclusion. So basically, if X is a simplicial complex, then if any set is in X, all its subsets are also in X. And the sets in X are usually called the faces of the simplicial complex. And a maximal face is called a facet. That is a face that is not contained strictly in a larger face. So for example, over here on the right, I have circled certain elements of the Boolean poset. And they form a simplicial complex, basically because below any circled element, everything is. And the highlighted ones, that is the singleton set 1 and the set that contains 2 and 3, are the facets of this simplicial complex. Okay, so we'll also need a geometric way of looking at simplicial complexes. And the way we do that is as follows. So for the simplicial complex, we choose a point for each vertex. So we choose a point in some Euclidean space for each vertex. And if a bunch of vertices forms a face, then those corresponding points in the Euclidean space form the vertex set of a simplex. So for example, here 1, 2, 3 is a face. So the vertices 1, 2, and 3 are the vertices of a two-dimensional simplex, a triangle. And similarly, here on the right, you'll have to imagine it in 3D. But 1, 2, 3, 4 is a face. So the vertices 1, 2, 3, and 4 form the vertices of a three-dimensional simplex, tetrahedron. So a simplicial complex is also a way of gluing simplices together in a nice way. Okay. So the simplicial complex that we'll be looking at, the way we define it is as follows. So you start with a permutation pi, written in one-line notation as usual. The simplicial complex X pi will have faces that correspond to increasing subsequences of pi. So for example, if pi is this permutation over here, 3, 2, 5, 4, 1, 7, 6, then 1, 3, 7 is a face of X pi, because if I look at the first term, the third term, and the seventh term, they form an increasing subsequence, 3, 5, 6. So 1, 3, 7 is an X pi. And similarly, you can find out what the other faces of X pi are. And it is clear that this is a simplicial complex. Now, for this particular permutation pi, this is the geometric view of X pi. So here, this part is a hollow octahedron. So sort of bipyramid, but it's hollow inside. And then there are these two lines sticking out, 6, 5, and 7, 5. And so if you collapse this line that joins 6 to 2 and 2 to 7, so if you sort of pinch it all to a point, you can see that this space becomes something that looks very much like the space on the right, which is S1 wedge S2. So the sphere of one dimension, that is the circle, and the sphere of two dimensions, the usual sphere, that are touching at a single point. And in topology, we usually say that these two spaces are homotopic. And so in general, a wedge of some topological spaces just means you choose a point in each of those spaces and identify them. So S1 wedge S2, you're just choosing a point in S1, choosing a point in S2, identify. And this is a special case of something that happens in general. If you start with any permutation pi, then X pi is homotopic to a wedge of spheres. And this flavor of result is very common in topological combinatorics. Okay, so now a bit of history about this topic. So the first place that these complexes were studied, not directly, was by this study by Pizhititsky and Silvero. So they studied a more general class of independence complexes of certain graphs, and the complexes that I talked about from permutations were not explicitly defined here, but they were in this 2020 study by Chokalski, Levi, and Meshel. So this was the first place where it was explicitly defined. And the most recent study about them was by Meshulam and Moyal, where they studied the average topological connectivity of such complexes. Okay, so the first thing that we noticed in this project was that there are certain patterns that play a special role in this context. So before going into that, I'll make a quick definition that probably a lot of you are familiar with, which is patterns and permutations. So to define them, I'm going to represent permutations using these sort of grid diagrams. And this is the common way you do it. So the first term is 4. So in the first column, on the 4th row, I put a dot. So the second entry is 2. So on the second column, in the second row, I put a dot, and so on. So this is the usual way we have this geometric representation of permutation. And we say that one permutation contains another. So in this case, this permutation 4, 2, 5, 6, 1, 3 contains 1, 3, 2. If I can choose 3 points. So here I've chosen these 3 red points. So I can choose 3 points. And if I delete all the rows and columns that don't touch those red points, I'll precisely get the diagram for 1, 3, 2. You can also think of it like this permutation has a subsequence that looks like 1, 3, 2. Okay, so this is the notion of pattern containment. So usually here, the smaller permutation that sits inside the larger one is called the pattern it contains. Okay, so the patterns that we'll be interested in are these cross patterns of dimension k. So I'm going to first define them. So CPK is just the sum of k plus 1 copies of 2. So by that, I just mean, for example, CP1, you have 1 copy of 2, 1, and then you just add another copy of 2, 1 above. So in the actual permutation is just 2, 1, 4, 3. Similarly, CP2, there are 3 copies of 2, 1. And so the permutation is 2, 1, 4, 3, 6, 5. So basically, first 2 you swap, second 2 you swap, third 2 you swap. So these are the permutations. And one thing that is not too hard to prove about these is that XCPK will be homotopic to SK. That is, if I look at this permutation complex for CPK, it will be homotopic to the sphere of dimension k. So this is why, if we go back to the previous slide, in the name we have of dimension k. And the cross pattern part comes from the fact that XCPK is in fact the boundary of what is called the cross polytope. Okay. So we have these permutations with this nice property. But what's interesting about them is these permutations are the only way in which you can construct spheres in this context. So more concretely, what I'm trying to say is that if you start with the permutation pi, and x pi is homotopic to this wedge of spheres, SK1, wedge SK2, and so on, then if pi avoids the pattern CPK, that is, if pi does not contain CPK, then all these values K1, K2, and so on must be strictly less than K. That is, pi cannot have SK in this wedge decomposition unless pi contains the pattern CPK. So sort of CPK is the only way in which you can construct the sphere of dimension k in this context. So this, I think, is a pretty nice result. But there is some good news and some bad news. And I thought this would be the nice time to show this quote by Charles Boyle from the TV show Brooklyn Nine-Nine. And just as Charles's grandmother suggests, we look at the bad news first and then the good news. So the bad news is probably something you would have expected, which is that the converse is not. So just because the permutation contains CPK doesn't mean in the wedge there is an SK or SK plus 1, K plus 2. It doesn't give a lower bound for the dimension of a sphere in the wedge decomposition. So for example, if I look at this permutation, 2, 1, 4, 3, 5, so it of course contains CP1. It in fact starts with 2, 1, 4, 3. But if you look at X pi, it becomes a contractible space. It's basically because of this 5 at the end. you can collapse the entire space onto that 0.5. And so this does not contain any spheres at all. So it's an empty wedge decomposition. So just because it contains CP1 doesn't mean it has to have an S1 or S2 or something. Okay, so the converse is not true. But the good news is that a sort of partial converse is true. That is, if pi contains certain types of occurrences of CPK, then this guarantees that SK occurs in this wedge decomposition. And for those of you more familiar with permutation patterns, these certain types of occurrences can be written down in terms of mesh patterns. So those are the figures that you see in the background. Okay. So I thought I'll end with a question and a generalization of this complex. So the question I have to say is my favorite thing to come out of this project, and it has to do with longest increasing subsequences. So this is a pretty popular topic. So longest increasing subsequence is basically an increasing subsequence of the largest possible length. Right? So in our context, these subsequences just correspond to facets of the largest possible cardinality in X pi. Right. So a longest increasing subsequence is the same as a facet of X pi, which has the largest possible cardinality. Now, there is this notion of purity in simplicial complexes, where a simplicial complex is said to be pure if all facets have the same cardinality. Now, in our context, if we look back at this correspondence over here, X pi being pure means, first of all, by definition, all facets have the same cardinality, which just means that all facets correspond to longest increasing subsequences. And since any face is contained in a facet, X pi being pure, purely combinatorially means that if you start with any increasing subsequence of pi, you can extend it to a longest increasing subsequence. That is, you start with any increasing subsequence, I'll be able to add terms to it so that it becomes a longest increasing subsequence. So this, I think, is a very nice property that a permutation can have. So the question is to try to characterize and count the permutations that have this property. Okay. Now, of course, there are several other questions that can also be asked, based on the topology of X pi, and for time constraints, I won't be able to go through them all. But I should also mention that we were able to answer these questions for certain classes of permutations. For example, permutations avoiding certain patterns, stuff like that. Okay, so I'll end with a generalization of this simplicial complex. And the way we'll generalize it is as follows. So when we were looking at X pi, we start with the permutation pi. And to make the faces, you basically collect all the increasing subsequences. Now you can think of increasing subsequence as subsequence avoiding 2, 1. So it avoids the pattern 2 because it's an increasing subsequence. Now we just generalize that 2, 1. So you fix a pattern sigma. And now the simplicial complex that we'll be looking at, X sigma pi, just consists of all subsequence that avoid now sigma. And if sigma is 2, 1, we get back the original simplicial complex that we were looking at. So we have just started looking at these simplicial complexes. And one thing that we were able to prove is that for the decreasing patterns, that is, if sigma is something like 5, 4, 3, 2, 1, or 3, 2, 1, some decreasing pattern, then this complex is again a wedge of spheres. Okay, so I thought with that I'll end, and thank you for listening.